Hey guys, we're going to start discussing some other periodic trends. We've talked about, the other parts of the periodic table. Now we're going to talk about some trends and patterns that we see that you may not be as familiar with. And there are three of these. The first one is atomic radius. And you guys are going to be responsible for remembering what the trend is, whether it decreases or increases in a certain uh, direction, and you're going to have to be able to explain why. That is important. You absolutely have to be able to explain why. So the first trend we're going to talk about is atomic radius. That is 1/2 the distance from the center to center of two like atoms. So if you have two different atoms here, and you find the center of each, it's half the distance between them. So that is your atomic radius. Let's talk about what happens in this trend. So the atomic radius group trend, and remember, group is going down the periodic table, same as a family, okay, a group. So here's the trend that you need to know. It increases from top to bottom. It's really important. So what we're saying is that as you go down the periodic table, you get an increase. This is because major energy levels 1 through 7 are being filled with more and more electrons. The electrons get farther and farther from the nucleus. Now, right now that's just words to you. I'm going to go to the next slide in a second and show you what I mean by this. So you might want to pause if you want to write this down and then go on to the next slide with me. So basically what happens is that, let's say we have lithium, sodium, potassium. So here's lithium, here's sodium, here's potassium. Okay, and these are in this group 1 going down the periodic table. Well, lithium is right here, and if you look, lithium has 2 energy levels. That was my nucleus in the middle, that weird thing. So here's its electrons. This might not be easy. Here's 1, 2, 3. Okay, so with only these 2 electrons keeping the positive nucleus from that valence electron, it's pretty easy for this positive nucleus to pull on these valence electrons and pull them closer to that positive nucleus because opposites attract. Now, when you go on to something like sodium, I'm just going to drop it over here so I have a little bit more space. Oops. Here's my positive nucleus. Now, sodium has 3 energy levels. 1, 2, 3. And sodium has 11 electrons. Oops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now you've got more space between this positive nucleus and that outer valence electron. So the size of the actual atom of sodium is larger than that of lithium. Okay, you have more energy levels. And then if we go on to potassium, you've got your positive nucleus here, and potassium has 4 energy levels. So these valence electrons are going to be way further from the nucleus. So because of the fact that you have more energy levels, you have a larger atom. So as you go down the periodic table, down a group, you have an increase in the size of your atoms. Now let's talk about across a period. Now, the way that I do my arrows is a little different than a lot of people do because it just makes a lot of sense to me. Oops, let me erase that. And I always go from right to left instead of left to right. So the atomic radius increases from right to left on the periodic table. So going this way, we get an increase in size. This shows a picture of some atoms and their atomic radius. As you can see, they're increasing. as they go from right to left. And this is because extra electrons are entering the same level while the nucleus gets larger and more positive, and that draws the electron cloud in towards the nucleus. And I'm going to explain what that means. Again, I'm going to draw a picture on the next slide for you. So if you want to pause and get this written down, go ahead. All right, so what happens here when I'm saying that we get an increase in size over here? If we think about this over, let's use oxygen. Here's oxygen over here, and oxygen has 8, well, I'll just do that, that's fine. 8 positive protons in its nucleus. It has 2 energy levels. So these electrons, 2, 3, 4, 5, 6, okay? There are 8 of these protons pulling on these valence electrons. So what it does is it pulls the radius in closer, okay? So these electrons get pulled in towards this positive nucleus, bringing this shell closer and closer in towards the nucleus. So that's oxygen. Whereas over here, if you have, let's say, lithium again, all right, lithium also has the same number of energy levels, but lithium only has 3 positive protons sitting here in the middle. So with those 3 positive protons and its 2 energy levels, these electrons don't have to hang out as close to the nucleus because those 3 protons have less pull on the valence electrons because there's only 3 of those protons to pull. Whereas over there with oxygen, there's 8 of them to pull on the valence electrons. So the more protons you have, the closer it's going to bring your valence electrons. So as we go from right to left on the periodic table, we are going to have an increase in size of atomic radius. All right, so what I generally show you is I have you draw it like this. You can just draw yourself a little reminder, and atomic radius increases. Here's the way that I remember that. Now, I would absolutely draw that in your notes for atomic radius. Okay, so the way I remember this, and one of the reasons I do my arrows this way, is that the plural of radius is radii with 2 i's, increase. It's a really handy way to make you remember your trend. So atomic radius, always going from right to left and top to bottom, increase. So let's look here and do some comparisons for some atoms. Let's say you have fluorine, zinc, and then calcium. Let's talk about which is, well, we'll do that. But let's talk about which is the largest and which is the smallest, okay? And to do that, I usually just draw my trend. I'll draw an arrow that way and an arrow that way. I'll label it so I don't forget. And then if I don't have a periodic table that I can write on, I'll just put these in the general place where they belong. So we know that we're increasing going over to the left and we're increasing going down. So that means that calcium here is going to be the largest. Obviously, if you turned your arrows around, that means going up you would decrease, and going this way you would decrease. So that means fluorine is the smallest. Hopefully that makes sense to you. Let's look at another example here real quick. So if I asked you what the largest element on the periodic table is, you're obviously going to tell me it's francium here. Let's say you have, hold on, make sure I do this right. Let's say you have chlorine and carbon. So we know our trend is increase. increase. Now, here's the thing. Carbon is one, so here's chlorine, here's carbon. 1, 2, 3, 4. Oops, I shouldn't have done that. Sorry. Hang on. Okay, if I start at chlorine, carbon is 1, 2, 3 spots over to the left. But carbon is only one spot up to the top, because these can get hard, because carbon should be increasing that way, but chlorine, if you're just looking at the trend down, chlorine would be larger. So you got to figure out which is more like, which has more space in between it. So the the horizontal has more space, if that makes sense. So carbon is going to be the larger atom here. All right, let's talk about ionization energy. Ionization energy is the energy that's needed to remove an electron from an atom. So you've got an atom here, and it's got its little valence electrons out here, and it is the energy it is going to take me as another atom to go in and steal that valence electron right there. How much energy is that going to take me to steal it? It's kind of the same idea of how strongly an atom holds onto its valence electrons. Okay, it's called ionization energy because when that electron is removed, both of the atoms become ions. That electron gets removed from this atom and it goes to another atom, so we have different numbers of electrons and they become charged with ions. So let's look at what happens for the ionization energy group trend going down the periodic table. We decrease from the top to the bottom. So if you guys are going to draw your trend, and I always draw my arrows, like I said, this way, we're going to decrease from top to bottom. And that's because the electrons are farther from the nucleus and field levels cause a shielding effect. And we'll talk about that in a second, and what that looks like. But you should know the definition for shielding effect as well. It's over here on the star. That means that the inner electrons shield the outer electrons from the positive nucleus. This means outer electrons are not held as tightly. So when you look, going down again, let's look at lithium versus sodium. Okay, lithium has its two energy levels. Here's your positive nucleus. Sodium has here's your positive nucleus, 1, 2, 3 energy levels, okay? Now, within these energy levels, lithium has these 2 electrons in there, and then it's 1 valence. Sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inner electrons, and it's 1 valence. So what happens is these inner electrons here, they shield that valence electron from that positive nucleus, okay? So what happens is the amount of energy it takes to remove the electron is going to decrease because this positive nucleus down here can't really hold on to its electron very well with all these other electrons in the way. So you're gonna, oh crap, no, that's right, I am talking about this way, never mind. So you're going to see a decrease in the amount of energy it would take me to come in and pluck this little electron here away from its nucleus. Here, there's only these 2 little electrons standing in the way of this valence electron. So it's going to take me a lot more energy to get this guy right here away from its positive nucleus. So with ionization energy, as far as its period trend, as you go from right to left, you're going to have a decrease. This is because the higher the atomic number, the more protons you have. The more protons means there's more positive charge in the nucleus to pull on the valence electrons. This makes it harder for another atom to steal those valence electrons, so it requires more ionization energy. I'm going to show you what that looks like. So with ionization energy, our trend is decrease, decrease when we draw our arrows like this. And when we're talking about the periods, let's take period 2, for example, and let's look. We have lithium here, and in its nucleus, lithium has 3 protons. That's not a 3+ charge. Its nucleus has a 3+ charge, but not overall. But it has 3 protons. Here it's electrons. There's 1, 2, 3. Then over here we have, let's say, oxygen. And oxygen has its 2. Let me draw that a little bit better. Okay, so oxygen has its nucleus and 2 energy levels. But oxygen has 8 electrons in here. So 8 positive electrons in here. And here are its electrons. 2, 3, 4, 5, 6, 7, 8. So oxygen has these 8 electrons to pull on those, those 8 protons to pull on those valence electrons. So since it has those 8 protons, positive, pulling on those valence electrons, it's got a stronger hold on them. So if I'm going to come in here, here I am, and I want to steal me an electron, well, it's going to be real hard to steal it from this guy up here who has these 8 protons. Wow, this is not working out how I wanted it to. Hold on. 8 protons. It's going to be a lot easier for me to come over here and steal it from this guy who only has 3 protons, who can't hold on to his electrons very well. So the more protons you have, the higher the ionization energy is. You need more energy to pull away those valence electrons. So that's why when we've got these higher atomic numbers over here on the period, we've got an increase in ionization energy, and over here we've got a decrease in ionization energy. So decrease, decrease. Remember to draw your arrows that way. Of course, if you flip the arrows, it would be increase, increase. So let's take a look at an example here. We'll say we have cesium and we have rhenium there, and we'll give it some astatine. So we know that we have a decrease and a decrease. So knowing that, we can put these in order of increasing ionization energy. So which one has the lowest ionization energy? Obviously, if we're decreasing across from right to left and decreasing down, cesium is going to have the lowest. And then we're going to have arsenic will be the highest ionization energy. If we did, let's see, let me go back to what I was kind of talking about before with you guys. If we had iodine right here, and not do phosphorus, iodine right here, and sulfur. And we want to talk about which one has the lowest ionization energy. Well, we know that it's going to decrease going this way. So if we're only talking about that way, sulfur would have the lowest. It's also going to decrease going down. If we're only talking about that way, then obviously iodine would have the lowest. But since we have to talk about both, we need to look at the fact that sulfur is only 1 over, but iodine is 2 down from sulfur. So that down is going to kind of win, and we're going to take that iodine has the lowest and sulfur has the highest on that one. Okay, the last trend is electronegativity. This is the ability of an atom to attract an electron when it's bonding. So this is just a picture of electronegativities on the periodic table. The blue are going to be low electronegativity, and red up here is going to be high electronegativity. The electronegativity group trend, so going down, we've got a decrease. It's the same trend as with ionization energy. The more energy levels, again, the reason is energy levels. The more energy levels that are added, the further the electrons are from the positive nucleus. So there is a shielding effect. This means that the nucleus has a weaker hold on its electrons. So this would look like, if we're talking about the periodic table here, here's our trend. It's decreasing, okay? So we'll say that we have our lithium here. Oops. We've got our lithium here, and lithium has 2 energy levels. Here are its little electrons. And then down here, we'll say we have potassium. Potassium, on the other hand, is in the same group, but it has 1, 2, 3, 4 energy levels. So of course its atomic radius was decreasing, going down. But now what we've got here, here's our positive nucleus, is these, I'm just going to put my valence out here. So again, this is the ability to take an electron. Well, here's the problem. The nucleus, the positive nucleus, if I have an electron just hanging out here in the world, the positive nucleus is what's going to attract the neutron, or sorry, the electron, because electrons are negative, the nucleus is positive with those protons. So if I have that electron sitting out there, who is more likely to be able to attract that electron? Well, obviously the lithium up here is, what did I say this was my potassium, because the electron only has to get through a couple of shells with only a couple of electrons in its way to try to push it out of the way. Whereas here, you've got all of these electrons hanging out in the way, shielding the nucleus. So the nucleus, that positive nucleus, has to overcome all of this in order to try to get this electron out here. Whereas this over here only has to overcome this little bit to try to get that electron out there. So electronegativity is going to decrease as you go down a group. The period trend for electronegativity is it decreases from right to left, just like ionization energy did. The number of protons in an atom that will attract and hold electrons close decreases as you go from right to left. Obviously, if you go the other way, you're increasing. So let's look at what that looks like. So here's our decrease, decrease. As we are going from right to left, over here with oxygen, we have 8 protons. With lithium, we have, it's 3 protons. So who is more likely to attract an electron? Well, the one with 8 proton is much more likely to attract an electron if we have one out here. So this is going to have a higher electronegativity. This one over here is going to have a low electronegativity because it has fewer protons to attract that negative electron. So we have our, with electronegativity, just like with ionization energy, our trend is decrease, decrease. So if we pick a few elements out of here, nickel, and there we go. All right, so let's talk about which one has the lowest electronegativity. Well, the trend going from right to left is going to be decreasing. So obviously, as we are going over this way, it's getting smaller. And then, of course, as we are going down this way, it's getting smaller. So Lu has the lowest electronegativity, whereas arsenic will have the highest electronegativity, and that's it. So let's just do a quick little recap here. We have 3 trends. I'm just going to do it over here on the side. We have, and I'm going to draw it with my arrows to make it easy on me, I have atomic radius. And remember, my trick is radii, the plural of radius. It increases, increases. The other two, if you can remember that one, the other two are easy. You've got ionization energy. It does the opposite, decrease, decrease. And then you've got electronegativity, decrease, decrease, decrease. So if it's not a radii with those two I's, it decreases, decreases. So again, you guys have to know the meanings of each of these. You have to know the trend, increase, increase, or decrease, decrease. And you have to be able to put them, to choose which element has the highest or lowest. But you also have to explain why to me. That's really important. So you need to make sure you understand why. At this point, you guys are going to take your lecture quiz. It's going to be worth 25 points. You can use this QR code here, or you can go into the PowerPoint that I posted and use the link below, or just type it into your computer, whichever is better for you. It is due by 8:15 a.m. tomorrow. That is on Wednesday. So let me know if you have any questions in the meantime, and I will see you guys in a couple of days. Thanks. Bye-bye.